Okay, today we're going to start with normal and tangential coordinates, although after this we're actually going to cover a third set of possible coordinates that we might choose. This is around about where I start losing people. Okay, a lot of people are pretty comfortable using I hat, j hat, regular x, y coordinates. People start to get a little uncomfortable when we talk about normal and tangential and then radial and transverse. So what I'm going to do is for both today and the next class, I'm going to compare each new coordinate system to the Cartesian coordinate system. Okay, just so we can compare and contrast what's going on between these different coordinate systems. All right, again, our coordinate systems, yep, question? Yes, I did just start recording. Yep, thanks, I appreciate it. Are coordinate systems something that's inherent to the problem, or is it our choice? You tell me.
Our choice.
Our choice. Now, that isn't to say that one choice really mean either lines of algebra might be shorter or longer, or the amount of trigonometry we have to do. I don't know about you, but if I have to do a whole boatload of trigonometry, I am somewhere in there. Okay, so if there is a coordinate system choice that I can make that reduces how much trig I have to do, I tend to be more likely to get that problem correct. All right. So, a particle moving along a curved path may be conveniently described using an NT, or normal tangential coordinate system, instead of the Cartesian coordinates. So I like to draw this picture of a particle moving along a path. This green thing here is the path. Along a path, you have to tell which direction is it going. Is it going to the right and up along that path, or is it going down to the left? And so that's why I add these arrows. This says this thing is moving up and to the right. The little blue dot is our particle, and I'm just showing it at two different instances in time. This is the particle. Okay, and you noticed I've drawn my Cartesian coordinate system on here. Now, I drew it down in the bottom left. Does it actually change anything if I maybe were to put it up here? Does it matter where positionally you put your coordinate system? Not really. It might change how you define the position vector, right? Because you need to give your position vector relative to that origin. But it doesn't really change much about velocity or acceleration. I could have also chosen a tilted Cartesian coordinate system. Might be a little bit of an odd choice, but it would be equally as valid if I had said, I'm going to choose I hat here, j hat there. That's still a Cartesian coordinate system, as long as we have the understanding that that coordinate system stays put. No matter what the particle does, that coordinate system stays right where it is. It stays fixed to the earth. Okay, that's a Cartesian coordinate system. To contrast, the normal and tangential coordinate system follows around our particle. Okay? I'm just going to go ahead and draw what that looks like, and we can talk about it more as we go. So our tangential direction, I'm going to label it as u hat t. I'll usually give unit vectors the letter u and then a subscript telling more about it. So that goes in the direction of motion tangent to the path. Pretty straightforward. Tangential is tangent, goes in the direction of motion. What has to be true about the other direction? Is there anything we might know about the other coordinate direction? Maybe relative to the tangential direction?
We want it to be perpendicular.
Aha, yes. So if I had done this and I said, aha, that's my normal direction, you would say, that's not a coordinate system. A coordinate system has to be made up of two perpendicular axes. So if they have to be perpendicular, that means I essentially have two choices. If this is the line perpendicular to the tangential direction, my u hat n either points up or points down. Okay, that limits the possibilities. Who knows which one is correct? Anyone do some reading ahead of time? No? Do your reading.
I know which one is correct, but I don't know why.
Tell me which one you think is correct.
Downwards.
Downwards. You are absolutely correct. The reason is because it points into the curve. So let's talk about what into the curve means. If I were to look at the curve at a point very, very, very close to the current location of my particle, and I fit a circle to that path right there that matched the curvature of that path right at that instant, that is what we would consider the curvature of the path. Okay, so if I draw a circle that matches the curvature right at that instant, the radius of that circle is what we call the radius of curvature of that path. And our normal direction points into that circle. Okay? So my normal points into that circle 90 degrees from my tangential direction. Let's do that at another spot just to solidify these ideas. Let's go to this later point down the line on the path. My tangential direction, is it the exact same direction as it was before? So if I were to take this vector and copy it and paste it over here, is that my tangential direction? No, it's not. It's no longer tangent to the path. I have a new tangent at this new point. Okay, so that means I need to redraw a new tangent. So I'm thinking tangent to this path looks more like this, u hat t. Okay. Now this, let's try to figure out the curvature circle or the circle that fits right here. I'm thinking this is a really wide circle right here, but it's on the left-hand side. It's kind of curved that way, right? So that means that my normal direction needs to point up to the center of that circle instead of pointing in the other direction. And it's still 90 degrees from our tangential direction. Okay, I'm going to put this in words. Here I'm going to say the u hat t is tangent to the path. And u hat n is perpendicular to u hat t and points into the curve. Remind me, these coordinate systems, they're made up of two different things. What is this that I've defined here? It's a certain type of vector.
Unit vector?
It's a unit vector, yes, absolutely. So you'll notice that I am using this little hat symbol. If I use this hat instead of, for instance, an arrow bar, this hat denotes a unit vector. This arrow denotes a vector more generally. Okay, so its magnitude might be greater or less than 1. Okay, so we know how this coordinate system moves. So that's one of the biggest differences between the normal tangential and the Cartesian coordinate system. Cartesian coordinate sits where it is. It's fixed to the Earth. It never moves no matter what the particle does. Whereas the normal tangential system is fixed to the particle. And it follows that particle through its path. And it changes and rotates as the particle moves along the path. So now we need to know, how do we define position, velocity, and acceleration relative to these new coordinates? All right, so what I'm going to show is on the left, the Cartesian position, velocity, and acceleration, what we covered a week ago now. And then on the right, I'll show how that changes for the NT coordinate system. So on the left, you'll see our position vector is the vector that connects from the origin of our XY coordinates to the particle's position. That red arrow is R. R is a vector. And we say that R has some amount Rx in the I hat direction and some amount Ry in the J hat direction. Okay. Now for our normal and tangential position, things get a little bit weirder. For normal and tangential, we define an origin of the path. So we define the start point of the path, and the position is then S, which is a distance along the path. So S of t is a scalar now, and it is the distance along the path from some position O. Okay, pretty big difference. We changed our definition of position from being a vector to a scalar. Okay, let's move on to velocity. Velocity is always what? What was it? Tangent to the path, absolutely. So no matter where I am or what coordinate system I use, the velocity vector is always going to look like this. This is my velocity vector. Whether we're using NT or Cartesian coordinates, this is my velocity vector. Tangent to the path. Okay, in Cartesian coordinates, I say that this is the time derivative of my r vector, or you can say that it has some amount vx in the I hat direction and some amount vy in the j hat direction. Let's go ahead and draw our NT coordinates on the right-hand side. So I know that my tangential coordinate is right here, u hat t. It's tangent to the path. What else is tangent to the path? Oh yeah, velocity. Oh, interesting. So they point in the exact same direction. Okay. All right, let's look at the curvature right here. I think the curvature right here looks kind of like this. So into the curve is this way, u hat n. Yeah.
Maybe I'm tripping, but what do you mean by into the curve?
Let's draw some extra pictures. let's talk about a very, very simple curve. Let's say you're in your car and you're doing donuts. Let's say this is the path you're traveling on. The radius of curvature of that path at any point is just the radius of that circle. Okay? Very, very simple for a perfectly circular path. But for a path that is not perfectly circular, it gets a little bit weird. Let's talk about a path that looks like maybe something like this, and we'll talk about here and here. If I'm at this point, position 1, if you were to draw a circle to try to match like this tiny little part of the path, teeny tiny little part of the path, right where that particle is right there, would you draw that circle here? Or would you draw that circle here? This one? Yeah, right. It's really easy to see here because this part of the path is nicely almost circular right there. So this is the curvature of that path. It's the circle that fits best right here.
Oh, it's just the arrow that goes to the center of the circle. Oh.
You got it. Right to the center of that circle. Is that better? Here's where it gets ugly though, is when it's not a nice tight curve. If we have a, maybe like that. Oh, almost straight line. The circle that fits best there, if I had to guess, I would still say it's maybe on this side, just because of the way this part is going. I'd say it's like some giant circle. Okay? The radius of that circle is going to be very, 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 very big. Right? So the tighter you're turning, the smaller the radius of curvature. The less tight you're curving, the bigger the radius of curvature. Okay? So here it's just barely able to tell that the normal direction is that way. What is the radius of curvature if I am absolutely completely straight? Any ideas? If I have a completely straight path, perfect line, what's the radius of curvature of this line right here? No. Remember, very, very, very small circle, very small radius of curvature means tight turn, very tight turn. Very, very big radius of curvature means barely any turning. How big can I get? I heard it. Infinite. Your radius of curvature is infinity for a straight line. Okay? That was good. Thank you so much for doing that. I appreciate it. Okay. I think we might be feeling a little bit better about radius of curvature now. Okay, let me clean this up a little bit because these are hard to tell which one they go with. U hat N. Okay, now let's try to write our velocity vector, v of t, in terms of u hat N and u hat t. So before, my unit vectors were I and j. Now my unit vectors, I'm going to write v of t equals to some amount in the u hat t direction plus some amount in the u hat n direction. All right. How much of v goes in the u hat t direction? All of it. Absolutely. Yeah, that's why I was making a big deal about the fact that this u hat t vector and the velocity vector are both completely tangent to the path. So that means that if I were to find the magnitude of my velocity, if I said, I can just refer to it as v without the arrow bar, I would say that entire magnitude of velocity goes in the u hat t direction, leaving 0 of the velocity going in the u hat n direction. So all of v goes in the direction of u hat t. None of it goes in the u hat n direction. And we want to relate it back to position. So I'll say this is where v, without the arrow bar, is equal to ds dt, where s is defined as above for position. Yes, ma'am.
For the v with the dsdt, are you referring to the magnitude?
Yes.
Okay.
Yes. It has to be, because s is what? A vector or a scalar? S is a scalar. So the time derivative of s is also a scalar. And so here v is the magnitude of the v vector, which is a scalar. Okay, so notice, one really important thing to notice, that red velocity vector, it did not change whatsoever from the left coordinate system to the right coordinate system. That is a property of the motion of the particle. I don't choose it, but I do choose the coordinate system. All right, let's go on ahead to acceleration. Normal tangential acceleration. All right, quick recap of Cartesian. Cartesian says I have some amount of acceleration that goes in the I hat direction, some amount of acceleration in the j hat. We can say that acceleration is the time derivative of the velocity vector, or the second derivative of the position vector. I'm going to put a particle over here on my normal tangential. And once again, nothing at all changes about that acceleration. Actually, let me belabor the point. I will copy it and paste it so that it can't change direction whatsoever. There we go. Okay, acceleration as a vector stays perfectly the same, but I get to choose what coordinates to express it in. Let's again draw our normal tangential coordinate system. Tangent is probably the easiest one. Goes tangent to the path in the direction of motion. I seem to be missing some arrows here. This particle is still moving up and to the right. Okay, if I were to try to figure out the curvature at that point, I would say we're probably curving this way. So my u hat n points to the center of curvature. U hat n. Okay, based on the way I've drawn it, does the acceleration vector fall entirely neatly into one of the unit vectors like it did for velocity? I'm seeing head shake no. That's correct. There's going to be some amount of acceleration that goes in the u hat t direction and some amount that goes in the u hat n direction. So it's not as nice and neat as it was for velocity. I'm going to go ahead, I'm not going to go through the proof of why this relationship holds, because it has to do with taking a time derivative of a vector that is moving through time. It has to do with the chain rule. Let me put it this way. I'll go through part of the explanation. So acceleration as a vector is still dv dt, but the way we've defined it, the way we've defined velocity in terms of nt coordinates, is that this would be the time derivative of v u hat t. Do we agree? I just substituted in what we defined for the v vector. Now, when we take a time derivative, it's all well and good if velocity is the magnitude of velocity is the only thing changing through time. But you've already told me that this u hat t vector also changes with time, right? It's moving, it's following that particle around the curve. It's not like our Cartesian coordinate system that stays in one spot forever and ever. No, it's changing direction. It's not changing magnitude, but it's constantly changing direction as the particle goes. So when we have a time derivative of two functions multiplied by each other that are both functions of time, what rule do we have to use for derivatives? Product rule. Yeah, we've got two things multiplying each other that are both dependent on that dt, right? So I would need to do the first times the derivative of the second plus the second times the derivative of the first. Something like that. And this is the part of the proof that gets really nasty, is trying to visualize what the heck is a time derivative of a unit vector. And I'm not going to go into all those details, okay? Just know that the reason that this relationship holds is because of a chain rule or a product rule of the unit vector itself, the fact that the unit vector itself is moving. Okay, so here's the definition we really need to know, which is here, I'll do it in red. Acceleration is equal to v dot u hat t plus v squared over rho u hat n. Yes?
So will rho be given from the problem?
We're going to talk about rho in more detail in just a second. If you absolutely need to find rho, I'm going to show you the expression that you would use to find it. What do you think rho is? In like words. I've said it like a bunch already. We talked about it here. Ah, that's why I did rho here. Rho is the radius of curvature of the path. Okay, and then v, you continue seeing this v without an arrow bar. What does v stand for? Our normal component of acceleration is equal to v squared over rho. What happens as we divide by a bigger and bigger and bigger number? It gets smaller and smaller and smaller?
0.
It goes to 0, absolutely. So our normal component will go to 0 as as the path becomes perfectly straight. So that means that acceleration as a vector will only have the tangential component to it. This goes to 0. Divide by infinity. Okay. Let's talk about what happens if we have constant speed. Does something else go to 0 if I have constant speed? All of acceleration?
The tangential acceleration.
Yes, just the tangential acceleration. Okay, so speed is that v, which is the magnitude of my velocity vector. That's speed. So if speed goes to 0, if I have acceleration is equal to v dot u hat t plus v squared over rho u hat n. If this is constant, it means it doesn't change in time. So dv dt is 0. So constant speed means dv dt equals 0, which is the same as v dot. So this term goes to 0, and we will only be left with a normal component. Okay, last but not least, I'm going to give you the expression for the radius of curvature. Now, this is only going to be useful if we are given the path as y equals a function of x. And I'm going to show you exactly what this means in the first example that we'll do, so I'm going to leave it as that for right now. So if we are given the path as y equals f of x, then rho we can find as 1 plus dy dx squared all to the 3/2 divided by d squared y dx squared. You will not need to memorize that. And this is an excellent question. Now we're starting to get into when you should start to familiarize yourself with what equations are you going to be given to you on exams. So that's why I upload my equation sheets right from the start. So they are up on Canvas right now. You know exactly what equations you'll have for exam 1. My best recommendation that I can give to you is to go ahead and print that out and have it with you every time you work on homework for this class. That will make it so that you know exactly how to interpret what's on the equation sheet and where everything is on the equation sheet, so you can get really fast at knowing, oh, I know I need this one formula, and I know it's on the page about here, and so you flip over and it's right there, and you know how to use it. You don't want the first time you're seeing that equation sheet to be when you're sitting in the exam. You should familiarize yourself with it now, okay? And I do believe I have radius of curvature on the equation sheet, but you can check. All right, let's hop into some work. Let's do a fun example. Okay, I have a nifty-gifty box that for whatever reason is riding along this nice parabolic path. I don't know why, it just is. It's flying through space along this parabolic path. So this box A, at this particular point, this point where x is equal to 2 and y is equal to 1.6. At that point, the speed of the box, speed of the box is 8 meters per second, and the rate of change of the speed is 4 meters per second squared. I want you to find the magnitude of the acceleration of the box at that same point. Now, after today, and probably as you start to attack your homework for this section, you're going to come across this question. You're going to need to be able to look at a problem and try to determine what is a smart decision for the coordinate system that I should use. For right now, let's just assume that we know that the normal and tangential coordinate system is going to be beneficial to us. But as you work through this problem, I want you to try to think about what are some clues that might be helpful to you ahead of time. Okay, so I'll give you one little piece of foreshadowing. The fact that the problem gives you this, it gives you y equals some function of x. That immediately tells me that I can calculate rho. That's exactly what I need in order to calculate rho. And rho is one piece of the expression that tells me how to write acceleration in terms of normal and tangential coordinates. Okay, so that is my first light bulb that normal and tangential coordinates might be useful for this problem. Okay, but for right now, here we go. We're going to say, all right, I'm going to set out and try to find acceleration in terms of u hat t and u hat n. And eventually I know that I'm going to need to take the magnitude of that vector. But I need to find that vector to start with before I can take the magnitude of it. Okay, now let's write out what is AT. What was that expression back in your notes? Flip back a page. Derivative, not of velocity, that would be v arrow dot. Yes, it would be the derivative of the speed. So it's v dot with no arrow bar. U hat t. And what is an? What is an equal to? Over rho, yes. V squared over rho. U hat n. Okay. This tells me that I have 3 quantities I need to go and find. 3 separate variables I need to go and find in order to fill this out. I need to figure out what the heck is v dot, what is v, and what is rho. If I know those 3 things, I can plug them in and I have acceleration as a vector. Do we agree? All right, who has any insight on what v dot might be? Yeah?
4 meters per second squared.
Beautiful. It's given to us in the problem. It says, okay, the time rate of change of the speed is 4 meters per second squared. This is a key skill in this class, is to be able to take the way that it's written in the problem statement and interpret it as the variables that you need in your equations. Okay, so it told us that if this is speed, this is the time derivative of that speed, we needed to recognize that that is the same as v dot. Okay, so v dot is 4 meters per second squared. All right, what is v? That's the speed. Yep, that's 8 meters per second. Oof, rho. They didn't give us that one, but they gave us a way to get to it, right? So let's go grab that equation that I had on the previous page. I'll go ahead and recreate it for you. This is 1 plus dy dx squared all to the 3 halves over, oh, I'm sorry. I think I wrote this wrong. These were not supposed to be square brackets. This is supposed to be an absolute value. I apologize. All right. Now, where does it give me this thing I'm supposed to take a derivative of? That equation in the top right? Y equals 0.4x squared. Okay, so if I want to fill this thing out here, I need to find dy dx, and I'll need to find d squared y dx squared. So the first and the second derivative of y with respect to x. Okay, so let's do the first derivative. 0.4 times 2 should be 0.8x. If I take another derivative of that, I think I get 0.8. Interesting. Notice that the slope still depends on x. But we really only care about one particular x value, right? What x value is it asking us about? Yeah, x equals to 2. Okay, so we'll go ahead and plug in x equals to 2. So this is equal to, is it 1.6? Is that right? Yes. Meters per second. Meters per second squared. This is meters. This is meters because remember it's a radius of a circle. So it's a distance. Okay, now I can plug back into my acceleration. So acceleration as a vector equals v dot u hat t, which should be 4 u hat t, plus v squared, which we said was, v was 8, so this is 8 squared over rho 8.396 u hat n. Is that what the problem asked me for? I need one more step, right? What do I need? We need to take the magnitude. Yep. So the magnitude of acceleration is equal to the square root of each component squared. Anyone want to master calculate that for me? Just another side note for exams as well, it's also really good for you to get used to using your own calculator. So try to use the same calculator every time you work on dynamics. Okay, that way you have memorized how to get from fractions to decimals and do your your trig and your inverse trig and all that. Okay. 8.608, I rounded to 8.61. Cool. All right, that's the problem. Questions so far? Did I lose you anywhere on this problem? Okay, I think this sets us up nicely to do our student-led problem. Okay, like I said, I like to do an easier problem first and a little bit harder. So I need to give you a couple of hints on this one before you'll really be able to get there. So in this example, again, we have a path, but this path is not given to us in terms of y as a function of x. Instead, it's kind of piecewise. We've got a line that connects A and B, and then a perfect circle, a part of a perfect circle between B and C. And then we don't actually worry about what happens after C, but we can assume that's a straight line too. Okay, so straight line, perfect circle, straight line. And we're given that a car with velocity, initial velocity of 30 meters per second, or sorry, that's not velocity, that's speed. An initial speed of 30 meters per second at A applies the brakes such that the acceleration in the tangential direction is minus 1/8 t meters per second squared. I want you to find the acceleration vector at C if the time it takes to get from A to C is 15 seconds. Okay, so I've already given you the one hint that this section is a straight line. And this section from B to C, that's terrible, but that's a circle. The other thing you might need to know is the arc length of a circle. Why do you think you would need to know the arc length of a circle? Yeah.
So you know the path length.
Yes. It's so that you can calculate the distance along the path, that position S that we described for NT coordinates. You can calculate that for the circular part of the path. Okay? So, our arc length of a circle is equal to the angle that you sweep through the circle, theta, times the radius of curvature of that circle, or the radius of that circle. Okay? Another interesting note in this problem, I'm giving you the angle that you're sweeping through. I'm telling you you sweep through 45 degrees, but I'm not telling you the radius of that circle. Okay, food for thought. Go ahead and start to take a stab at it. I'll give you a few minutes to try. I'll wait and see when it seems like people are getting bogged down, and then I'll start to add hints. Okay? Go for it. All right, my very first hint is where do you even get started? And that step is actually 100% the same from this problem as it was last problem. First, you're going to have to, later on, you'll have to recognize what coordinate system is a good choice. But for today, we're going to assume you know that the normal tangential coordinate system is a good choice. Once you decide that, you want to write down the expression for the acceleration vector in terms of normal and tangential coordinates. Okay, so that's what I've done here. I said, all right, I am on the search for this. I know that if I want an expression for acceleration, I need to fill out this. Okay? Then that tells me that there are 3 other subcomponents that I need to go hunt for. I need to figure out what is V dot. I need to figure out what is V. I need to figure out what is rho. What makes this problem a little gross is that it's piecewise. So there's kind of 2 parts. And acceleration is going to change from when you're on the straightaway to when you're in the curve. Okay, so you might think about it as 2 separate problems almost. There's one expression for acceleration when you're on the straightaway and a different one for when you're on the curve. Okay, go ahead and talk to your neighbors, see if they have any extra insights to offer. Yeah.
So like,
Adding what?
Like, okay, from A to B, it would be just the V dot as far as you have and from B to C, it would be different. So, like, would you add like the
No, you're not adding it. I would say it's asking you specifically about acceleration at point C. Okay, so let's say we're writing down acceleration at C. This is already given to you in the problem, right? You need to find this, which is v squared over rho. So you're going to have to do some extra math to figure out what is the speed at C. And you'll have to do a little extra math to figure out what is the radius of curvature at C. Yep.
So it fx would
So we already have that. So yeah. And then when did you have to like do it like
All right, I'm going to start adding in some notes here. Okay, V dot. What is V dot? It was sneakily given to you in the problem statement. Yeah? I see some head shakes. They gave you this, AT. They said AT, the tangential component of acceleration is minus 1/8 t, was it squared? No, t, minus 1/8 t. What is the tangential component? Why is my husband calling me? People need to leave me alone. Okay, I can plug in tangential acceleration. Tangential acceleration we know an expression for. 0, 15, minus 1/8 t dt, oh, that makes me scared. That I wonder if that was daycare. Yeah. We have, no, I'm not going to do that. We have 5 minutes. She'll try 5 minutes. Okay, equals v. I'll go ahead and put the bounds on here. I'm skipping a couple steps on that integration, okay? All right, so now let's do this integration. T squared 1 over 16 bounds from 0 to 15 equals v final minus 30. Simply for the sake of time, I'll let you know that v final is equal to 16 meters per second. All right. The last thing I need to know, we said I need 3 things in order to fill out acceleration. I need v dot, I need v, and I need rho. How might I figure out rho? Well, it was kind of suspicious that Dr. Higgins gave us an extra equation that included rho, so maybe that might be useful. So what if we have the arc length equals to rho theta, and we know that theta is equal to 45 degrees, or 1/8 of a circle, which is also pi over 4 in radians. If we want to know the radius of curvature, if I knew the distance along the path, I could solve for radius of curvature is equal to arc length over theta. Okay, how might I figure out that arc length? Or that distance along the path? Sorry? So the equation we used before was only if the path was given to us in terms of a function of y and x.
You gotta go to the position.
Yeah, we got to go back to the definition of position for normal and tangential coordinates. So if we go back, we should see that speed is equal to ds dt. Okay, so now we can again separate variables. V dt equals ds, integrate, and I want to integrate from initial time to final time. So initial position, 0, final position, SF. All right, let's see, do we have an expression for V? We would if we had continued to carry this through. I would have had V as a function of time is equal to minus t squared over 16 plus 30. Yep. Okay, so now I need to integrate 0 to 15 minus t squared over 16 plus 30 dt equals integral of 1 is just the variable, 0 to SF. Should be able to take that integral and find that my distance along the path from point 0 to from point A to point C is equal to 380 meters. So that's from point A to point C. That's not what we want. That's not the arc length of the circle. That includes the straightaway. So we need to subtract out the 100 meters from the straightaway to get the arc length of the circle. Okay, so this is equal, 380 is equal to 100 plus S arc length. So S arc length is 280. Plug back into rho, that should be 280 over pi over 4. Notice I'm using radians here. Equals 356 meters. I now have all 3 components that I need to find acceleration, right? I have rho, I have v, I have v dot if I plug in for 15. If I plug in 15, I get minus 1.87 meters per second squared. If you want to go through more slowly and check your answer, acceleration at t equals 15 is equal to minus 1.87 u hat t plus 16 squared over 356 u hat n. All right, we're right on time. I apologize, that was a rush at the end. I hate that. But it will be uploaded for you to review.